Celinski.
Thank you very much. It's a lot of light, so I don't wonder if we can put some maybe down a little bit. But let me tell you what I would like to talk to you about today. I would like to give you some feel how one can characterize magnetic materials and tell you why they are important. And I will illustrate this characterization which was performed, let's say, for the examples I'm going to show you in our lab in Colorado Springs, basically last year. But before I start, let me tell you a little bit about our department. We have now PhD programs, so our area of specialization is basically condensed matter physics. We also do a little bit work in, actually starting right now, in biophysics. And since it's very close to you, you may actually consider this if you are interested in the graduate program. The things which is really good in our case is the fact that we have very small classes. Typical graduate classes we have is between 5 to 15 students. To give you an idea, I'm right now teaching second semester of solid state physics, and I have 4 students in my graduate class. So you're gonna get a lot of attention from the professor. We have faculties which are fairly widely recognized as good teachers, and we really have excellent facilities. I have to say, from the point of view what is available in my lab, I have MBE, sputtering system, ultra-high vacuum evaporator, all these characterizations. This is magneto-optical Kerr effect, ferromagnetic resonance. I have the whole set of systems which can measure properties of materials up to 110 gigahertz in terms of devices, so on wafer. So from the point of view of high frequency characterization, the lab which I direct is one of the best in the United States in terms of equipment. But let me give you the overview what I would like to talk today about. First, I would like to motivate why magnetic materials are interested, and then I'm going to illustrate this characterization of magnetic materials on this particular ferrites, which is a barium iron ferrites doped with aluminum, and I'm going to show you how, using structural characterization, magnetic characterization, and then high frequency characterization, we can understand behavior of a system. And when we do understand materials, we can use them in devices. In this particular case, this barium hexaferrite is a material which we would like to use for on-wafer microwave devices which operates above 35 gigahertz. So everything which goes to space or military system, and in the future probably to the commercial application, will be based on this material. So therefore this material is quite important for this kind of application. So what is the aim when we make magnetic materials? What we want to do is to control their magnetic properties. And if you think about magnetic materials, you probably don't realize one thing: how important they are in our life. If you think about semiconductor industry, which makes these processors and many, many different chips, this industry is relatively small compared to the industry associated with magnetic materials. Because every time you take your camera, there is some small engine which has to run. So there is something which has magnetic elements. Every time you take your old type iPod, there will be tiny hard disk. Each computer contains hard disk, or maybe not now because they are moving to solid states. But there are new applications coming in terms of magnetic memories, which are non-volatile and therefore very fast. Finally, there are certain applications which really require operation in a very harsh environment. So if you are in space and you have a silicon chip which is used for memory, this is not good, because due to radiation, the silicon can be easily damaged. So what you like to do, you would like to have a memory which is purely based on metals. And how are you going to build memory based on metals? Well, you're going to use magnetic materials to make memories based on spin torque devices, where you are sending the current through the nanopillars, and you can reorient orientation of magnetic layers, and therefore measure tiny changes of resistivity on the order of maybe 30%, and this determines the state of memory between 1 and 0. So the magnetic materials are with us on everyday basis. So basically what I'm going to do, I'm going to illustrate this characterization, in our case, how one can control one of the type of anisotropy in the spheroid films. Let me first tell you about how you make this particular ferrites, which is a very simple method. So when you are making devices, when you are making materials, the first things which you would like to do is to come up with a method which can be used on mass production. I mean, if you are using some very fancy tools like molecular beam epitaxy to grow something, these pieces of equipment are extremely expensive because they operate in ultra high vacuum, and therefore if you make devices, and we do actually, the element has to be expensive. So if you can come up with a method which you can create materials, let's say in ambient condition, and which is cheap, then this has potentials for going into the commercial products. So one of the things what we do is to use so-called metallo-organic decomposition technique. This is a very simple method because we are starting with a silicon wafer. We put a little bit of platinum. We anneal this platinum such a way that we are getting 1-1-1 texture, and I'm going to tell you about it a little more in the moment. And then we put some liquid, which has a precursor of this compound. And we are annealing it. First things we spin coat it. In other words, there is like a centrifuge which spins the wafer. You put few drops, the liquid spreads out, and you are forming liquid film. And then what you do with this liquid film, you put it in the hot plate, and you, in these temperatures, 150, 250, and 400, and you are solidifying it. At this temperature, you are removing the solvent, and then you are making at 250 and 400 this particular compound. And after this is done, you put these things into the rapid thermal annealing unit. So it's like a oven with halogen lamps, and you can ramp these things to 1000 Celsius probably within 1 minute in the nitrogen or oxygen atmosphere, in our case both, but first with nitrogen and then oxygen, and you are forming solid film in the time, let's say, of 10 minutes. You are basically done. And because the vacuum is not involved, this is the very cheap method. Now this method, yes?
Did you say you were removing when it was hot? You said it was removing something?
Yeah, basically what you are doing is, because you are starting with a liquid, yes, it's like a precursor. So this precursor has a lot of, it's a metallo-organic decomposition, which means that you have liquid which has a lot of carbon and hydrogen, and from time to time there is some metal ligand which contains barium or iron, yes? And therefore, what you do, this you cannot just put only barium and iron. There must be a lot of solvent. We are using, for example, nanoacetobutylene. Some chemists will know what this crap is, but basically it's something which is quite volatile, and it is being removed evaporates by this first step. So you are forming suddenly you are left with this metallo-organic base compound which contains barium and iron. And so it contains also a lot of carbon. So when you are going to 250 or 400 Celsius, what you are doing, this carbon is basically becoming carbon dioxide, and it just flies away. And what is left on a wafer is then pure barium and iron. But because there is oxygen, this oxygen starts to react with these two metals, forming this composition. And therefore it's a very cheap method. Now, you would ask, is this method used by anyone else? Absolutely. For example, not in the United States, but in Japan, they have something what is called smart card. And the smart card contain contain ferroelectrics, which are actually produced exactly the same fashion. So you can put some ferroelectric precursor and heat it up and forming ferroelectric film, and then you can pattern this film and to form ferroelectric memories. And this is a very cheap method because it does not involve vacuum. Yes?
I'm sorry, so in the conventional method, they put the wafer in a
vacuum.
High vacuum, and how
Yeah.
did they achieve that barium?
If you think in terms of how the semiconductors are made, how the devices are made, yes, how the memories are made, the easiest things to do materials, the most controlled fashion is by putting them into the sputtering system, yes? In other words, you put the wafer into the vacuum system. Typical vacuum system in the industrial setting is on the order 10 to the minus 9 torr. And so every time you put the wafer in, you have to load it in from the air to this 10 to the minus 9, so it takes time. Then you have to handle it with some robots within the ultra-high vacuum. Everything is very complicated. It's not cheap. I mean, each sputtering system which we are talking, let's say if you go to work for Atmel here in southern part of Colorado Springs, each sputtering system is about $1.5 million, yes? And you have zillions of them. I mean, if you think about how much it costs to make fab for processors, we are talking about expenses on the order of $4 billion for one factory. Yes?
So this is just nitrogen purge oven basically?
Exactly. So if you can make your active elements in the very controllable fashion, eventually what actually we do when we do devices, we pattern these things and we do metallization using, of course, sputtering system. But this step is very, very simple. So this is the reason why this method is very, very important. So rapid thermal annealing is used in the industry a lot. But okay, so I have now a layer, and then I have to come up with a determination what this layer actually is. So what we do, we use X-ray diffraction, and what I pick up here is a very simple picture which all of you recognize. I have basically coming X-ray. They are being reflected from the layer. I have condition, Bragg condition, which determines what is the thickness of individual layer, and depending on what kind of structure I have, all the information about my film is hidden into this D, which is the spacing between the layers. And of course, as a physicist, we determine what is the relation between a lattice spacing, and if you study solid state, you probably know what is the relation for cubic materials. For hexagonal materials, the situation is a little more complicated. Nevertheless, from the position of the peaks, in other words, position where the angle, I have a constructive interference for given angle, I can determine the composition and arrangement of atoms in our film. And this is basically done in X-ray diffractometer. I'm sending the X-ray, I'm measuring detector, and basically what I'm measuring the intensity as a function of this 2 theta angle. This is the schematic, picture of such diffractometer. So what you have here is an example of the films which we have actually made. And so let me start maybe with this red stuff. So what you see here, the red, is just a scan of silicon wafer with platinum on it. So I have a series of peaks here, and so I know what is my background. And then I'm growing my films on top of it, and I see the extra peaks which appears. And if you look at these numbers here, all of them have a type of orientation which we call 00L. It means that all my reflection comes, in this particular case, from the planes which are oriented such way that my C-axis is normal to my substrate. Now the film, the structure of this film is a little more complicated than you would imagine. I mean, this is how this unit cell look like. So we have a lot of these atoms here, many irons, 12 of them, barium, and a lot of oxygens. And basically from the X-ray diffraction, we are able to determine the position of each atom. Now,
so you grind your sample. I know it's powder.
No. This is not grinding. What you are referring to is so-called powder diffraction. So powder diffraction, when you are measuring materials, you are taking bulk materials, making some powder of it. Typical element size is on the order of maybe couple microns, and then you press them together, and this way when you do the scan, you see all possible reflections because these grains are randomly distributed. If you look back to this picture, what we have here only are these 00L reflections. All other reflections are gone. In other words, what I'm trying to tell you is that I'm forming the film. At this moment, I'm not telling if it's polycrystalline or not, which all the material is oriented in one direction. Yes? And therefore, what's happening here is, from these measurements, I can only determine the C lattice constant. My material is hexagonal, and what we actually have done, we have done very careful analysis by measuring with the angle theta between the normal of the samples and also measuring this thing at certain angle. So we were able to pick up, for example, reflection from the 0014. So one more time, we measured this position of this peak as a function of composition, and were able to determine the C lattice constant. And you see how the C lattice is changing as a aluminum concentration. And we also went out of the plane, basically doing the other scan, and was able to pick up the peak 0300 and also measure the A constant, because our lattice is hexagonal, and therefore we have two parameters which describe the structure. Now, what is really interesting is in these measurements, if you look at these numbers, yes, so here the numbers are in nanometers. So if you look here, we are measuring something which is on the order of picometers. This is our resolution with which we can measure the lattice constant. Now, if you think about it, it's really amazing that we can do this with such accuracy, because average atom size is on the order of maybe 0.2 nanometers, yes? So we can detect extremely small changes in lattice constants using X-rays. So the stuff which is around for the more than 100 years is still used very, very effectively to determine composition and position of the atoms in the samples which we study. Another method which we use is atomic force microscopy, and just to give you a very brief overview how this thing works. Basically, you have some tip, silicon tip, which is very sharp. You bring it to the sample, and then basically what you do, you bring it and you just tap with a tip your sample, and then the piezo element, so ferroelectric actually crystal, moves this tip along the sample, and by tapping all the time we can determine the surface morphology of our sample. The way this is done is basically the laser diode is shining on the back of the tip, the light is reflected, and because we have the photodiode which has 4 quadrants, we can determine how the light is moving on the, and from this we can determine the morphology. So let me show you the example of the studies which we have done on this aluminum doped hexagonal ferrites, and I have here 4 composition. Unfortunately I didn't put the composition for each photograph, but this one first is without any aluminum, and so you can see here, you can see very nice hexagonals, yes? Basically what I'm saying is that when this sample grows, it grows such way that this hexagonal structure is, the C-axis of hexagonals is perpendicular to the substrate, and I have polycrystalline sample, but the orientation of all the C-axis is normal to the substrate. As I'm adding more and more aluminum, so this is X equals 0.5, this is 1, and this one is, I believe, 2, you can see how the morphology is changing. That if I have a lot of aluminum, the shape of my grains is different. Now, the next things what we would like to do, we would like to correlate how such morphology is related to the magnetic properties. But before I do, I would like to show you one thing. If you look at this, for example, grain, you can see that it has like series of terraces. Yes. So let's look at one of a grain. And here is the one of a grain, and I'm basically measuring what is the change of height along the terraces. And you can see this is 4.6, then I have a drop. So I'm going from here to here, I have a drop to 2.3, another drop to basically 0, another drop to 2.3, and so on and so on. Now let me remind you that I showed you this data a few moments ago. Sorry, this one. That when we measure the lattice constant of our thing is 2.3 nanometers. In other words, each of the stars which I was showing you is 1 unit of our basic crystal. Now, is it always like this? The answer is no. Actually, there is a histogram of many different samples. Maybe, I don't know, my students probably took 10 of them and measure what are the size of the steps. So some of them are below 1 nano. Actually, this is in the unit of C. So this is 3/4, 1, 1 1/4, 1.5, and so on. So you can see the biggest drop we had was 4 1/4. But so we can have really small steps. So what really is happening is we have extremely flat terraces and then nice step down from terrace to terrace. It's really interesting what can we see with such instrument. But let's keep going about the AFM for a moment. So what I want to show you is this is basically the image of the film, and basically what you see, these are the morphology of the sample. The scale which we are talking about here is on the order of 500 nanometers. So what is the difference between this image and this one? Well, turns out in this particular case, for this image, what we have done, we have taken our tip and changed it to the tip which is partly covered with cobalt. So suddenly I have made magnetic tip. And this is so-called virgin material. It means that material after it was grown was never exposed to any magnetic field. And so what's happening is this two different contrast tells me about what orientation of magnetization or magnetic moments I have in individual grains. So if you look at, for example, this nice semicircle here, these are these grains. And they form one large magnetic domain when the moment in all the grains points up. But this one here, this grain here, the moments points down. So basically I can image using AFM the magnetic structure of our grains. What is really interesting is that these grains are relatively large, something on the order of maybe close to the half of a micron, but I never form magnetic domain or domain wall within the grain. It tells me that the anisotropes in this material is so strong that I cannot form domains in the individual grains. I will tell you about these things a little more later when I will discuss anisotropy and what it is. So let's go to the now magnetic materials. And so there are two ways we study magnetic materials. One of them is to study them in static magnetic fields, or the fields which are in the frequency regime, well, let's say up to 1 megahertz or so. And if we do this, we can determine a lot of very important parameters. One of the parameters which is really important is magnetization. So if I have a magnetic moment which is given by, oops, something cut me my S here. my figure, I guess. So this magnetic moment of the individual atom is given by G, Bohr magnetor, and S, which is unfortunately cut out here. Sorry for this. And this determines the moment on single iron atom. Magnetization is basically the ratio between the moments I have within the volume of my unit cell divided by the volume. So there are two important parameters which determines behavior of magnetic material. One of them is what is the maximum value of M, so-called saturation magnetization. So when I apply very strong magnetic field for this hexagonal structure, I'm going to reach certain maximum value of saturation magnetization. And if I change the direction, the behavior is very, very different. This simply tells me that this particular sample is very anisotropic. Depending on the direction which I'm performing measurements, I have different value of M. This is what basically in some particular application is extremely important. In other, it's actually non-desire. I've told you that, maybe I will come back to this in a moment. So basically what we want to know is how this material behaves in the different orientation. And second things which we would like to determine is what is the ordering temperature. Because if the material which we are making is non-magnetic at room temperature, its usefulness immediately drops down. In other words, very rarely we are using materials which operates in liquid nitrogen or helium temperatures. So what determines TC is related to the strength of the coupling between two moments in neighbor atoms, and this is a purely quantum mechanical effect. What determines these differences between the saturation magnetization in different direction is purely associated with relativistic effects. Now, if you think about it, magnetic materials are the only things which you can see quantum mechanics and relativity at the same time. Because what determines this difference is associated with anisotropy, and this is associated with the fact that electron orbits around the nuclei, and there is a coupling between spin and this orbital motion. And this what basically influence your anisotropy. Okay, let's move on. What is important is I have the differences, and therefore I must have some anisotropy energy associated with my magnetic system. This anisotropy energy typically is measured with respect to a certain direction, in this case c-axis, and certain constant. Every time you have you have energy of a magnetic system, you have effective field associated with it. I mean, what you remember from your undergraduate studies is that if I'm thinking about magnetic moment, if I multiply M dotted to B with a minus sign, I have energy. This is what we call Zeeman energy, and the effective field which we are talking about is just B. Yes? If I have different form of energy, like the one here, and I take derivative with respect to the angle, I'm gonna have some effective field which is given by this expression. So if this Ku is large, then my effective field is very large. Now, what kind of application you may have in magnetic materials? Let me just go. If you have hysteresis loop, so this is basically what you measure for magnetic material as a function of the applied field, you have something what is called saturation, which I talk about, and there is something what is called remanence. Yes, the remanence simply tells you what is the value of magnetization after you went from high field to zero field. For some application, you would like to have this hysteresis loop without any surface area. This is something what is extremely important if you think about it, because How you get your electricity to your house? Well, there is somewhere a generator which makes electricity, yes, but then it has to be sent to your house. Typically it's sent maybe at 110 kilovolts, and then comes down to the city is coming down to 25 kilovolts, maybe then 408, maybe 10, 5, but eventually in your neighborhood you have 480 volts lines, which then are come down again using transformer to 220 and 110. Actually 208, let's say, because 110 is just two different taps in 3 phases. If this hysteresis loop would be much wider, then you would lose energy every time you go through the cycle 60 times a second. And this would generate a lot of losses. So if you, depending on your application, your hysteresis loop defines what kind of material you need to have. If you want to use it for transformer, you would like to have hysteresis loop as with coercivity and remanent field as small as possible, basically 0. We are losing in the United States, I don't know, between 10 to 15% of all the energy we generate just by sending it from the places we produce it to the place we use it. Now think about it, 10% of all the energy is becoming a heat, which we don't want. It's a huge amount, yes, so therefore knowing what kind of materials you want to use is extremely important. But on the other hand, if you would like to have a hard magnet, this is not very good magnet, yes, you would like to have something which actually looks like this, because then actually the best would be if this actually go even more in this direction and has coercivity somewhere here. This example which I have here is, I believe, from cobalt. So cobalt is not perfect, very good hard magnet. So you would like to have a hysteresis loop which is much wider and much better defined. And there are materials which actually have this behavior. I'm going to show you that one of them is actually hexagonal ferrite. It was used as a hard magnet many, many years ago. By now we have materials which are much better. So magnetometry, we would like to know how can we measure this kind of behavior. So there are a few different instruments which one can use in the lab. Actually, I have all 3 of them in my lab. We have vibrating sample magnetometer, we have a squid magnetometer, and finally we have magneto-optical Kerr effect, which we use for study of very thin layers. The VSM is actually a very simple instrument, because what it is, it's a glass rod with a magnetic sample attached to it. It has a loudspeaker attached to the top, which drives these things up and down. There are some coils. Because this magnetic material is moving within the coil, it generates voltage. This voltage is basically associated with the Faraday law. So you have certain change of the flux, magnetic flux. This change of magnetic flux tells you how much magnetic material I have inside, and therefore I can determine, if I do this measurement between the pole pieces of electromagnet as a function of the applied field, I can determine the behavior of my material, basically measuring hysteresis loop. Another things which we have in our lab, oops, still not wrong slide, is squid magnetometer, and here we are using the fact that the sample basically also move up and down between these superconductive coils, and I can measure again how much moment I have moving between these 2 superconductive coils. Why we are using two different devices? Because squid magnetometer is at least 3 orders of magnitude more sensitive than the VSM. So if the sample is very tiny, the squid magnetometer is going to give me very precise measurements. And I'm going to show you the measurements using both instruments. So let's start with the hexagonal ferrites, and let's start with one example of measurements of hysteresis loops made using the squid magnetometer. So what you see here is a hysteresis loop which has relatively large remanence, And then if I'm changing the orientation of applied magnetic field from being normal to the sample, which is this one, to the being in plane, I have very different behavior. And if you look at this, I have to apply the field on the order of almost 2 Tesla, 20 kilogauss, to saturate my material. It means that my anisotropy field is on this order. It's on the order of just below 2 Tesla in this particular sample. If I change composition, this thing is changing. Actually, this sample has much stronger the anisotropy field than this one, and you can see the difference between aluminum content in this two sample. So just changing aluminum content in this compound, I can change anisotropies. What is important here? What are important from the device point of view is that I can increase effective anisotropy with increasing aluminum content, and I can also have my hysteresis loop, which is very squared. Because this means that if I'm here, when I initially magnetize my sample and come here at 0 field, let's say here maybe it's easier to see, I will be still almost at the full saturation. And therefore my material will be stable, will not demagnetize the way other films could. So what is shown on this graph is the ratio of MR, remanence magnetization, versus saturation magnetization. And you can see that for this particular sample, as a function of temperature, so we did measurements from basically 4 Kelvin up to 400 Kelvin in this case. There is some linear dependence. I mean, there is some dependence. But if you look at the numbers, these numbers are very small. So the squareness, the ratio is changing between 87 and let's say 83.5 or so. So it's really, the change is very minute. But because the squid magnetometer is so accurate, we can measure it very precisely. What is, however, changing not so small is coercive field. Coercive field is there a pen? Coercive field is this thing which we measure on a hysteresis loop. Is basically this value of a field. So if you look at this coercive field is increasing as a function of temperature. So at 400 Kelvin, it's on the order of 5.5 kiloerstat. At low temperatures, it's on the order of 3.5. So it's a significant change. So basically what the conclusion here is, we have high value of remanence, and also we have, let me click one more time, significant decrease in MS, because what I'm showing here is how magnetic moment is changing as a function of temperature. So at low temperature, I can force all the moments to be aligned with the magnetic field. As I'm going to the higher and higher temperatures, the moment, saturation moment, which I'm measuring is far below the value at 0 Kelvin. And the reason for this is very simple. I have vibration in my lattice. This phonons which goes around and kick magnetization out, they misalign it, and therefore what I measure at let's say room temperature is reduced by 35%. So this is something which I also have to keep in mind when I'm designing my materials for particular applications. So what is shown here on this graph, so far I was only showing you individual examples, but here we have combined changes in very systematic fashion, having with material with no aluminum whatsoever to the high content of aluminum when aluminum content was 2. And you can see how this thing is changing. So basically what I'm plotting here is the coercive field as a function of temperature, and what is measured here is the squareness. This S is the ratio of MR to MS as a function of temperature. And you can see, if I don't take the material which is pure barium hexaferrite, which has significant change. The rest of the materials basically behave in the very predictable fashion, and they are temperature independent. So again, if I have application which goes to space, because it has to be on a satellite, if I'm changing the temperature, I will not observe any changes in my behavior of my device, and this is something what again is important. So high value of remanence and significant decrease of MS. Finally, there is a picture here which shows how the moment is changing as a function of composition, in this case in temperature, and you can see that is basically going down with increasing aluminum content. And in a sense it's understandable, because if you put non-magnetic atom in the place of magnetic atom, eventually what has to happen is the net moment has to go down. And this is exactly what we observe here. So of course we've done all the systematic measurements of this for all the samples, and you can clearly see that initial this decrease is very small, up to maybe 75, 80 Kelvin, and then is basically going linearly down. These measurements were done with the squid magnetometer. Actually, all the data which I have shown you so far were done with the squid magnetometer. But squid magnetometer can only measure, at least our one, the one which we have, can only measure up to 400 Kelvin. So if we want to see what's happening in higher temperature, we have to go to use VSM. And so what you see here is an individual magnetic moment as a function of temperature for one particular composition, x equals 0.75, and you see that eventually moment is vanishing. This determines the transition temperature for this particular compound. So what I'm plotting here is Tc as a function of composition, and you can basically see it's fairly linear, up to 125, and then it's a little deviation. And this is actually quite interesting that such deviation happened, because people have speculated and suggested that if we have small concentration of aluminium, the aluminium will preferentially go to one of the sites which I have showed you on the previous graph, but above certain concentration it goes randomly to some random sites, and therefore we have deviation of Tc in this respect. Okay, so this is basically the conclusion, that the linear decrease of temperature. Now, everything what I have told you so far was about static measurements. So now what we would like to do, we would like to see how these materials behave in high frequency. In order to do this, you have to use series of techniques. One of them is ferromagnetic resonance, and I'm going to talk a little bit about it. We are actually also using this vector analyzer FMR. We have Brilliant light scattering in our lab, but none of the data which I'm going to show you today were done with BLS. And there are other techniques like time resolved MOC, which we also have. Pulse inductive microwave magnetometer is the system which I was helping building at NIST a couple years ago, 10 years ago actually. So let's talk about what's happened if you expose material to high frequency. So let's start with something very simple, things which you know. If I have the displacement in a system where I can displace my mass out of equilibrium, I'm going to get the standard equation which all of you recognize, Hooke's law, yes? And basically the solution for this are certain oscillation of my position of my mass, and this depends on the strength of my spring and mass. So this is how material is gonna behave in such situation. What's gonna happen if I have a magnetic material? What's gonna happen is I have basically the same system. I'm gonna have a magnetic moment which gonna oscillate around the direction of the applied field. Now, this applied field is not necessarily only field which you apply external field, but it could be also one of these effective fields, these anisotropy fields, and therefore depending what is this value, I may have faster or slower precession around the direction of this effective field. So in magnetic materials, what we actually measure, we measure the change of angular momentum with respect to the time. And this determines the torque. So as I've mentioned previously, the connection between the magnetic moment and field is following. The magnetic moment is Bohr magnetron, then G factor, and then S. This is my magnetic moment of the single atom. If I have applied field, there will be a torque acting on my magnetization, which again, this is something what you remember from the undergraduate physics. Now, what is the relation between this moment and magnetization? I'm going to tell you in a moment, but let me start with this torque equation. So basically, if I have moment in the magnetic field, I'm going to have certain torque. This torque is going to change my system, and I'm going to have a precession. Now, this system doesn't have any inertia. In other words, if I switch off my magnetic field, the system should come to equilibrium instantaneously. And you feel that this cannot be right. There must be something which will keep these things going and maybe reach some equilibrium in certain time. Now, it turns out that for metallic materials, the system will go to equilibrium maybe in 10 to minus 10 seconds or so, because this is how strong the damping is, and I'm going to show you how this thing is related to coming to the equilibrium. So what's happening is that basically if I have this torque equation, I can start with something which describes the component of each component of a moment, and if my H is applied along the Z direction, and here are my components of my magnetization, my moment, sorry, not magnetization, I can solve this very simple determinant and find out what is the relation for change of mx or my and mz. Mz you can clearly see will be 0, but mx and my will not be 0. So let's start with the ferromagnetic resonance. What do I have? I have some moment, and I'm applying big magnetic field. So this moment will have tendency to process around the direction of the applied field. Now imagine that in the direction perpendicular to this DC field, I apply some RF field. If this thing is processing and this thing is oscillating, if the frequency of oscillation of my magnetization agree with this RF frequency, I'm going to resonantly absorb energy. It's exactly like you have in your grandma's house. This is my favorite example. When you have a windows in your grandma's house, the house is old, the windows are not very good, and they can basically vibrate. So when you have a truck passing by in a street, this window simply gives you this buzz. And what's really happening is this acoustic wave comes in, is being absorbed by the windows vibrates, absorbs energy, and your grandma can hear this nice buzz and she's annoyed, yes? Exactly the same thing's happening here. I have this precession and I have this oscillation, and if this oscillation agree with my natural precession frequency, then I resonantly absorb energy. If I look at the relation here, is that the change of the angular momentum is given by m cross effective fields. Now the relation is that the J, angular momentum, is related to magnetization by this factor gamma. So if I can replace J with this expression, I'm going to get Landau-Lifshitz equation. Now this equation is exactly the equation I showed you before, but now instead of talking about moment, I'm talking about magnetization. In other words, I'm talking about moment per volume. What is really important, and this is the power of FMR, that what is here in this HF is not only applied external field, but all the possible effective fields associated with any form of energy I have in my system. So if I take derivative of this energy with respect to magnetization, I'm going to get the value of this effective field. So when I'm studying my samples with magnetization, I can determine all anisotropy fields. So this is basically the message I would like you to get out of this talk, that if we have a form of magnetic energy, there is effective field associated with it, and we can measure it. So this is the reason why we have measured very precisely this MS, because if MS is changing as a function of temperature, my anisotropy field will also change, even if the anisotropy constant is constant, basically, as a function of temperature. So let me just bring all the equations. They are in different form. I can talk about, in ferromagnetic resonance, about torque equation, which are in two different forms. This one with the Gilbert form, this is the Landau-Lifshitz form. But this term here determines the damping. In other words, when we had this precession, if I'm driving the system in, this thing's gonna oscillate. But if I'm delivering more and more energy, it's gonna process with a bigger and bigger angle. This is not what is happening in the system actually. What is happening is this cone angle is actually quite constant for the reason that there is a damping in the system. In other words, what damping wants to do, the damping wants to bring this magnetization along the direction of the applied field. So the damping is a very important parameters which we have to keep in mind when we do this studies using FMR. There is another way of thinking of it, that you can determine the frequency of your oscillation by basically minimizing the energy with respect to the angles in your sample. And if you think about it, it's also quite natural, yes, because if I have some potential well and I have a system exactly on the bottom and I bring it slightly back, I have basically parabolic dependence of my energy, and therefore what I'm going to have oscillations which resemble standard harmonic oscillator. This is the reason why I brought you this example of the mass on a spring, because it's exactly the same behavior. If I go out of equilibrium, there is a restoring force which brings this system back to the minimum of energy. Okay, this is enough about theory of this. Let me only tell you what kind of anisotropies we can measure. We can measure uniaxial out-of-plane anisotropy, shape anisotropy, which you probably have heard of, maybe not with the magnetic system, but definitely with the dielectric system or ferroelectric system. There is uniaxial in-plane anisotropy, fourfold cubic, many of them. And if I do measurements as a function of angles, I can determine all of them and determine different contribution, for example, associated with the surfaces, associated with exchange coupling to other magnetic materials. All these things can be determined with the dynamic measurements. The ferromagnetic resonance system is fairly complicated actually. This is an example of the system I was using when I was a PhD student. But I have a microwave system which brings energy down, and then this energy is being absorbed. So I have certain amount of energy coming down is being reflected. So what I'm measuring is actually I'm measuring the changes in reflective signal. This is much simpler system. I mean, schematic diagram. What's happening? The wave comes in, is being reflected. If it's absorbed as a function of the applied DC field, I can measure this changes through the directional coupler. So this is what we do in FMR measurements. Believe it or not, these are actually measurements which I have done many years ago on some iron films. It's a beautiful Lorentzian curve, and what we can determine out of this measurement is position maximum absorption, which determines resonance field. I can determine the width, and I can also determine the surface area under this curve, which basically allows me to determine following parameters. From the resonance field position, I'm determining magnetic anisotropies. From the line width, relaxation, or in other words, damping. And from the intensity, how much magnetic material actually I have in my film. What we very frequently do, we don't measure these measurements like this. We measure the derivative. Again, you have here examples of the dots represent the measured points, and the solid line is a fit. And you can connect this line with the width of this double dip curve to the Gilbert parameter which determines the damping. Anyhow, so I hope that I have convinced you that this is something what is quite powerful. What we do when we do measurements right now, we are using very modern equipment. This is a vector network analyzer, stuff which can send, let's say in this particular case, a microwave up to 70 gigahertz, and I'm sending this microwave along some structure. I'm putting my sample here, and then I'm taking the signal back, and I can determine using the transmission properties of our films. So let's actually show you the results of a ferromagnetic resonance as a function of applied field for one particular composition. So you can see that I have different ferromagnetic resonance frequencies at the different values of the field. If I solve my Landau-Lifshitz equation, basically this is a relation. This is a relation which tells me what is the frequency and how frequency is associated with the applied field, anisotropy field, and the saturation magnetization. So having such formula now, I can analyze this data. From the slope, I can determine the gamma. From the intercept, I can determine this parameter HA minus 4 pi ms. So if I know effective saturation magnetization, I can determine again anisotropy field. And yeah, as you can clearly see, this is fairly nicely linear behavior. Here is an example of the line width, and again we can measure the line width in our films, and we can determine that these peaks are really Lorentzian shape and they have relatively low damping because the line width is very, very relatively small. So what is here is basically showing you results for all the samples which we have measured. Now look what is very interesting. If I'm taking the sample which doesn't have any aluminum, I have this behavior. But if I put in my formula x equal 2 aluminum, I can only measure this amount because my system operates up to 70 gigahertz in this particular case. So you can immediately see that by changing the composition, I'm changing this anisotropy field significantly, yes? So what is plotted here is an effective anisotropy field as a function of composition, and you can see how it changes from 1.3, let's say, Tesla up to 2.5 Tesla. So this material can be used as a fairly good permanent magnet. Actually, our goal is completely different. We want to use it for microwave devices, but nevertheless. Okay. Another thing what we have done, so this is the figure which you have seen before, and now I'm actually plotting. I analyze all this data and I can now plot anisotropy field as a function of temperature. And you can see how by changing composition, how bigger and bigger this anisotropy field is getting depending on the composition. So now if I want to have device operating, let's say, in zero field at 55 gigahertz, I would probably use something which looks like this green dot, which is 1.25 composition. So if by changing composition, I can make device to operate at particular frequency at a ferromagnetic resonance. So again, now you have seen this graph. I know now what is my anisotropy fields, and I know what my magnetization is, so I can calculate my anisotropy constant. And so out of this, what you can see is that I have some trend. With the increasing temperature, anisotropy constant is getting smaller. But if you look at this data, they are so scattered that basically there is no correlation between composition and value of anisotropy field. What this simply tells you is that the anisotropy, that the change of the anisotropy field is purely governed by how saturation magnetization is changing. And therefore, we have made basically the circle. We started with the static magnetic measurements. We determined what saturation magnetization is. We did all the measurements in high frequencies. And then we come back with this data, static data, to determine how anisotropy constant is changing as a function of temperature, and basically determine that the anisotropy field, this difference between sample with x equals 0 to sample x equals 2, is purely governed by ms. I will maybe skip these things because we are already, this is about, I have last more slide. What we have here is basically showing you how this alpha in the Landau-Lifshitz equation is changing as a function of composition. So I have very small damping, relatively small damping for the small content of aluminum. As I'm increasing it, it's getting bigger and bigger. And then above 1.25, I have big jump, and I cannot measure it anymore. Anyhow, so to basically summarize this talk, I hope that I could show you how using different magnetic techniques one can fully characterize this hexagonal ferrites doped with aluminum and then determine how good they are for this particular application. What we are doing with this film is not only growing them, but we are also interested in, for example, combining these films with the different ferroelectrics. Because if I can form the heterostructure where I have a ferroelectric and ferromagnetic materials, by applying voltage, maybe I can change magnetic properties. It's much easier to change voltage than change magnetic field. On this, I'll thank you for your attention. Thanks. Questions?
Okay,
Please.
What exactly do you mean tune devices electric field?
So if you have a magnetic material, if you want to change something, typically what you do, you apply magnetic field, because then the system will respond to the applied field. But imagine that you have a heterostructure, where one layer is magnetic, second is ferroelectric. And there is a coupling between these two layers. And you apply the voltage between the bottom here and top of this my ferroelectric film. You can change polarization of this ferroelectric, and therefore possibly change the magnetic materials. To give you a trivial example, think about material like PZT. Yes, it's not this one, but PZT is it's a ferroelectric which has big piezo effect. So if you are applying the voltage, you are changing physically the size of this film. Therefore, this film on the top gonna act on this one by pushing it down. Suddenly you are changing physical dimension of your magnetic film. If you change physical dimension, there is something what is called magnetostriction. You are changing magnetic materials by changing the physical size of your film. Basically, you are squeezing, for example, the C-axis, and therefore you are changing properties of your magnetic materials. So this is what we would like to do. The thing is, to change electric field is very easy. You have function generators which can gives you any waveform you want in the nanosecond regime without any problems. Actually, picosecond. Let's be honest. We are talking about maybe 50 picosecond or so. To change magnetic field, you have to have electromagnet. There is a big inductor which you have to change the current. This thing takes time. So if you want to very quickly tune your device, doing this with magnetic field is very ineffective, very expensive from the energetical point of view. You have to change the current. If you can change just voltage, this is very quick response.
Got one more.
Yes.
So you use your platinum as a template to,
yes.
to grow the
hexagonal ferrites, yeah.
Okay, that one, yeah. Okay, so why platinum? Because that thing's expensive. I can understand it makes a good template, but is there any other method to use?
One platinum for two reasons. We are growing these films, and we are annealing them in rapid thermal annealing unit up to 1000 Tesla. So if you put different metal than platinum, you're going to anneal it. Sorry, you're going to oxidize it instantaneously. So this is the reason why platinum. Now, from the point of view of cost, this is nothing. I mean, it's true. The target of platinum, which is, I think we are using target which is 4-inch. It's about $15,000 per target. It lasts maybe a year or so. But from the point of the industry, this is nothing, because amount of the material which you are putting is on the order of, let's say, even micron or two. This is what we would like to actually do. Okay, so it's fraction of a dollar.
So that's why you chose platinum.
Yes.
Does platinum have any electron behavior that is beneficial to the substrate?
The platinum has one nice feature, which is that when you are growing it on a silicon, and actually we are growing it on a silicon which is thermally oxidized. In other words, there is a layer of silicon dioxide, glass, on the top of the silicon wafer, which is 5,000 or 10,000 angstrom thick. The platinum, when you grow on it, on this amorphous layer on the glass, and when you anneal it, it's becoming reoriented. All the grains are pointing in one direction. So you are getting very nice texture, which you can grow when your hexagonals, ferrites, very well. We tried different materials. I mean, we tried, for example, combination of moly and platinum, and it didn't work. Basically, the moly was alloying with platinum and basically causing the problem. The platinum has one big disadvantage, which is platinum is not very conductive. It's not copper, and we wish to have the higher conductivity, because this immediately determines what kind of skin depth you have in your devices. I mean, you know that if I'm sending the electromagnetic wave towards the metal, the electromagnetic wave is going to penetrate to certain depth and then is reflected. The skin depth, this penetration depth, is determined by two parameters. One of them is conductivity, and one of them is frequency. Both are like inverse square of the square root of the sigma conductivity and frequency. So the higher the frequency, the thinner the skin depth is. The smaller the conductivity, the bigger the skin depth is. In other words, your metallization layer is not very good. It doesn't contain the wave. It's basically letting this wave to leak out, which is bad, because then you have losses. So all these things has to be taken into account when you are designing the system. But the only things which you can come up with so far is platinum. I don't want to go to other very exotic materials like ruthenium or other crap, osmium, because it's simply even more expensive. Any other questions? Yes.
When you have saturation, is that mainly in the electrons, in the orbitals, and their behavior?
Yes. In other words, if you have a magnetic ion, yes, like iron. I mean, why certain atoms are magnetic and other are not? What's the difference between the copper and iron? And the pure difference is amount of electrons you have in 3D shell. In other words, for iron, this 3D shell is not completely filled up, and these moments are really very well localized, and therefore their orbit has particular shape. So you can if you look at for example, open your quantum mechanics book and look at the d orbitals for the 3D metals. They are their density of electrons is very high in very small area, otherwise it's basically falling up very rapidly. So they have very peculiar shapes, not like s electrons, which are basically spheres, or p electrons, which looks like this kind of shapes, yes, eights, and so on. So when you apply magnetic field, you are really forcing these electrons to be aligned in the direction of the applied field. Now, I've mentioned to you one thing, that they are processing along the direction of the applied field. Why they are processing? Well, what's happening is you have this atom, and imagine that there are thermal vibration. So this moment is pointing in this direction. Here is thermal vibration coming in, phonon, hits this thing, comes out, and what this thing does is process to the equilibrium position. For metal, it typically takes one round of one precession. Dumping is so large. For other materials, like yttrium, iron, garnets, this precession can last microseconds. So it's incredible difference. No question from students?
Well, I think sometimes you covered in class.
Anyhow, I hope that I gave you show you some excitement, which is still in the studies of magnetic materials, because this is still relatively large field. And we had a Nobel Prize a few years ago when Peter Grimberg and Albert Hurt got the Nobel Prize for the work on the GMR, giant magnetoresistance, which is used in every computer nowadays, reading heads.
No, we definitely done that. So. Completely exciting. And I think the students really appreciate it to see the real life, you know.
We only have this little, as far as optical goes, that shows that magnetic domains you have
Yes.
to look in the microscope.
Yeah, so this is bubble memory is probably what you have, which is showing how the domain walls can move in the applied DC field.
So is that related to that Kerr effect?
This is related to Kerr effect in the following fashion, that in the Kerr effect, what you measure in the Kerr effect is basically change of polarization of the light. So imagine following scenario that you have, this is my electric field of my light which comes in. And I have here magnetization pointing in this direction. And so what's going to happen is when the light passes through the material with magnetization pointing in this direction, the light plane of polarization is going to slightly rotate. These changes are very minute. We are talking about fraction of the angle, of a degree, okay? And so this light propagates, changes the plane of polarization, and what you measure in your system, you are measuring typically you have polarizer and analyzer. In other words, you are measuring in cross-polarized system when one polarizer is in this direction, second is perpendicular to it. And therefore, you see any small changes in the polarization of the light. Now, if you think about it, what's happening in this particular case is something like this, yes? That you have your film. Let me maybe do it differently. Here is the entire film, and you see some funny shapes here, yes? This is what you probably see in your bubble memory. Dark and white regions. So what's happened is the light goes in with the polarization like this, propagates through, and then in different areas, depend what is orientation of magnetization, the plane of polarization is slightly rotated or not. If it's rotated, you see this as a difference in intensity, and therefore you think that this is dark and white. I mean, these changes are really minute. Of course, everything is a function of distance through which light is traveled. If you work in the transmission, this is so-called Faraday effect. If you work in the reflection, like we typically do, it's a Kerr effect. But yes, absolutely.
Hey, one more question.
Sure.
That's when you had those crystals, and then you said you did we were showing the
Domains?
Domains. And you said they're mostly confined to the crystals?
Yeah, to the particular grain, yes.
Yeah. So is that always true? Is it saying
Typically it's not.
No.
But typically, so again, what determines the domain structure? Domain structure is determined by two parameters. If you have, imagine that you have just two grains, yes? One of grain has moment like this. So what this thing does, it generates fields which are dipolar fields, yes? So if I put another grain here, what these things would like to do is do this. I will have up and down, yes? In other words, this is exactly what we are talking about here. That I have one region here with a moment like this, I have this behavior. So if I put another magnetic region here, it would like to have magnetization like this. Now, so in other words, your sample wants to be demagnetized. But in order to do this, you have to change. So if you have a continuous material, yes, you have spins going like this. They are coupled by exchange coupling, and you have to change orientation of this spin to this orientation. Now, I'm talking now about quantum mechanical effect. Yes, I'm talking about how I'm making the angle between the Si and Si plus 1. So this costs you a lot of energy, because this Hamiltonian for this thing is given by minus j S1 dotted to S2. So you can clearly see, if I have two spins, if they are both parallel and this thing is positive, this minimizes my energy. If I now have, so this is what's happening in ferromagnets. Yes, I have all the moments parallel. Now, if I change orientation of one of a spin, this I'm gonna increase energy. I'm gonna get out of this minimum up, and therefore the system doesn't want to do this. And so what determines the position of how wide this transition is. In other words, in the region, not like here, but in the standard materials, what you have to do, you have to go from this orientation to something which maybe looks like this. And this region here, I call domain wall. Domain wall width is determined by how strong anisotropy field is. In other words, if the anisotropy field is very strong, the domain wall will be very small. I will go from one orientation to another. In material like iron, I need about 1,000 angstrom, so 500 atoms, to go from one orientation to another. Therefore, iron is a soft material, anisotropies are small. In stuff like this, the anisotropies are so strong that within the given grain, I have never domain wall, because anisotropy simply prevents them to form. But if I have two independent grains, like this one and this one, when they demagnetize, in other words, this is this picture here, when one grain is up, this one can be down, because it doesn't cost the system energy whatsoever. So this is why this thing is happening.
So can you control this, where your moments are in the same, and then you have your field that switches them over to the other? Can you control that, and that's how you would relay like 0-1 information for computers?
Absolutely. I mean, in computers, if you think about it, what's happening in the hard disk? Yes, in the hard disk you have basically continuous magnetic material still, but they consist of very tiny grains. Okay, these grains are coupled by interaction. So what's happening is, imagine that you are writing the information with applying some strong magnetic field, and all these moments suddenly are like this, in one direction. Now, the picture which I gave you here is probably very accurate. In other words, people have about 15 tiny physical grains of material which are coupled, forming one bit. And then you have another one when you can write these things down. Yes, so you have moment like this, and you have here reading head, which consists of two different materials. Let's say like this. One of them is always, let's say like this, up. Second is soft, can switch between being up or being down. Okay. So these layers can flip. Now imagine that you are driving the current which goes here, and you are picking up here. Depending on orientation of this layer, if it's up, you have one value of resistance. If it's down, you have higher values. I will take it back. So as a function of a position x, you're gonna have something which looks like this, and this represents your 0, 1, 0, 1, and sometimes you have 0, 0, 1, 1, 1, and so on. Yes. Actually, the situation is a little more complicated than this, but in principle, this is what's happening. So this is how modern computers read, by reorienting one so-called soft layer in the reading heads. And these materials, I mean, this anisotropy field in these things nowadays, in modern product, are on the order of 5 kilo Ersted. So in other words, 0.5 Tesla. It's starting to be a big problem, not to read information, but to write it. Because imagine you have to deliver impulse of a field to the region which is maybe, let's say, 10 nanometers by 20, on the order of half of a Tesla. This reading head flies about between 1 to 2 nanometers above the surface of a disk.
How many? What? How much?
1 or 2 nanometers.
Oh.
So imagine the Boeing 747 flying 1 centimeter above the ground, because this is basically the comparison. They have even wings, so they fly properly. I'm not teasing you, it's true. It's aerodynamic is involved.
Wow, this is really fascinating.
I have one question.
Sure.
To tell the students, this is for the students. And that is, how strong is the magnetic field, say, around the inner electron orbits?
Okay. So this is a very good question. So you remember I wrote this Hamiltonian, which is minus j s1 dotted to s2, yes? You can think of it as something like minus s1 times j s2, yes? When you can treat this as a field. The field in iron is on the order of 2000 Tesla. This is the field.
I was saying in some of the neutron stars.
Yeah, in the neutron star, the fields are even higher. Any other questions?
We're also taking quantum mechanics, so that should. Yeah. Well, I think you did kind of take our breath away from us. No, thank you very much.
You are very welcome.